students, welcome to the channel. In this video, we are going to talk about isomerism in coordination compounds. In part 1 of this video, we already have spoken about structural isomerism. So in this video, we'll be focusing on the stereoisomerism in complex compounds. So let's get started. The stereoisomerism basically deals with three-dimensional arrangement of ligands around the central metal atom. So the stereoisomerism is further classified into two types. The first one is geometrical isomerism and the second one is optical isomerism. Let's get started with geometrical isomerism first. So geometrical isomerism, you must have already studied this in general organic chemistry class 11. You get to see this kind of isomerism in organic molecules also. But back then, for a molecule to exhibit geometrical isomerism, there needs to be a carbon-carbon double bond, and you used to talk about the position of the atoms around these two carbons involved in this double bond. So if you were having same type of groups on the same side, you would call it as cis isomerism. If you are having different type of groups on the same side like this, you would call it as trans isomerism, isn't it? So cis isomerism and trans isomerism is two types of geometrical isomerism. But this is what you studied in organic chemistry, isn't it? So in organic chemistry, this is trans and this is cis, because you have same groups on the same side and different groups on the same side. Now, there are a few points which are similar in case of complex compounds as well, but then there are a few points which are dissimilar, and let us talk about both of them one after other. In case of complex compounds, for a molecule to exhibit geometrical isomerism, this double bond is not needed. You don't need to have carbon-carbon double bond over here. Instead, you will be considering this entire unit as a central atom. So you will be having central metal at the center taking the place of this carbon-carbon double bond. And you still talk about the arrangement of the groups around this central atom. If you are talking about a complex which is consisting of 4 ligands of this fashion, this is the central atom and B is the ligand and AB4 is the type of complex that you are talking about. In this kind of complexes, the central atom is at the center, let's call it as A, and you are talking about arrangement of these groups around the central atom. Since all the 4 ligands that you have here are same to same, it's no point talking about same groups present on the one side or different groups present on one side. It is the same groups any side of the central atom, right? So this cis trans isomerism or this geometrical isomerism is not applied for those complexes in which you have got all same type of ligands. This kind of complexes are called as homoleptic complexes. So this geometrical isomerism is not applied to homoleptic complexes. Rather, it is applied to heteroleptic complexes, as in the complexes which contain ligands of two types. For example, a complex with a central atom, and this is having 2 ligands of one type and 2 ligands of another type. In this kind of ligands, you get to see geometrical isomerism. So coming to the conditions required for geometrical isomerism in complex compounds, condition number 1, you need to have a heteroleptic complex. You need to have at least 2 types of ligands surrounding the central atom, and the second requirement is the coordination number should be either 4 or 6. Coordination number of the complex should be 4. So you should at least have 4 ligands to observe geometrical isomerism, or you should have 6 ligands to observe geometrical isomerism. Let us take one example to understand this geometrical isomerism better. Look at this molecule. So these examples I have picked up from NCERT itself. Example number 1, a platinum complex wherein you are having 2 NH3 ligands and 2 Cl2 ligands. This looks like a typo in the textbook. The square bracket should cover platinum as well. So this is the entire complex. And I'm placing the central atom here, platinum, and since you are having 2 types of ligands, one is ammonia and the other one is chlorine, you try arranging these ligands around the central atom as you want. You try arranging it. So there are 2 possibilities of this arrangement. Possibility number 1 is you taking both the chlorines on the left hand side and both the ammonia groups on the right hand side. Possibility number 2 is taking 1 chlorine and 1 ammonia on each side. Other than these 2 possibilities, other than possibility number 1 and possibility number 2, you check and tell me if there is any other possibility. If you are now going to say that we can also arrange it in this way, platinum over here, ammonia in this place, chlorine in this place, and chlorine in this place, and ammonia in this place. If you're going to ask me about this arrangement, look, in this arrangement also you have one ammonia and one chlorine on one side, one ammonia and one chlorine on other side. So technically speaking, in this arrangement that you suggested, you have placed two groups of different type on the left hand side and two groups of different type on the right hand side, which is similar to what have I done in arrangement number 2. So in conclusion, if you are having a complex of this fashion, if you are having a complex whose coordination number is equal to 4 and which is having two ligands of one type and two ligands of other type, in this combination, this is the only way of arrangement. You can either arrange it in fashion 1 or you can either arrange it in fashion 2. That's it. There's no third arrangement possible. Alright. So now you observe these two arrangements. In arrangement number 1, when I take the vertical line and observe, on one side I have the groups of same type and on other side I have the groups of different type. And in arrangement number 2, on the left hand side I have the groups of different type and on right hand side also the same. So when you consider the vertical line, vertical imaginary line passing through the central metal, and when you observe the position of the groups, if you get to see same groups on the left hand side and same groups on the right hand side, or if you get to see same type of groups arranged on the same side, you call this isomer as cis isomer. And if you see the opposite, like on the left hand side I have the groups of different type arranged and on the right hand side I have the groups of different type arranged, then I call this kind of arrangement as trans isomer. So geometrical isomers can be cis trans isomers. If they are cis trans isomers, these are the conditions required to be followed. The complex need to be heteroleptic complex and it should have coordination number to be 4 or 6. If it is having coordination number to be 4, this is the possible way of arranging ligands around the central atom. And if you are arranging in this manner, there are two things that can happen. One, you can have same groups arranged on the same side along the vertical line, or you might have different groups arranged on the same side along the vertical line. If you have same groups arranged on the same side, then you call it as cis isomer. If you have different groups arranged on the same side, you call it as trans isomer. So basically you have cis isomer and trans isomer existing for this particular complex. Alright, I hope this point is clear with you. But in case of any doubts, you can ask me your doubts in the comment section below. Now let's talk about what if I have a complex whose coordination number is equal to 6. When you have complex whose coordination number is equal to 6, you might have three different possibilities. Possibility number 1, maybe it is a platinum complex, for example, and you are having all the 6 ligands being of same type. You call this as homoleptic complex, and homoleptic complexes are not eligible for geometrical or cis trans isomerism, so you can't consider this. Then the second possibility, you might have the central atom, one ligand of 3 count and the second ligand of 3 count. When you have two ligands in 3 plus 3 combination, cis trans isomerism in this kind of ligands is not possible. We'll have some other type of geometrical isomerism seen here. So even this combination, this 3 plus 3 combination of ligands doesn't work. And now moving on to third kind of arrangement, you are having platinum acting as central atom. Ligand A taken 4 times, ligand B taken 2 times. Over here it is 4 plus 2 combination, 4 ligands of same type, 2 ligands of same type. And in the second case it was 3 plus 3 combination, 3 ligands of same type and 3 ligands of other type. So this combination is not valid for cis trans isomerism, but 4 plus 2 combination is valid. It also can be written as 2 plus 4, 2 ligands of A type and 4 ligands of B type also work. In this case you get to see cis trans isomerism. So if you are talking about observing cis trans or geometrical isomerism, in this case there are two conditions. The complex need to be heteroleptic by nature and it might have coordination number 4 or 6. If you are talking about coordination number 4, there are no problems at all. But if you are talking about coordination number 6, in coordination number 6, this combination does not work for cis trans isomerism. You need to look for 2 plus 4 or 4 plus 2 combination. Let's take one such example. Observe this. You are having cobalt NH3 taken 4 times in Cl2. In this complex, you are having central atom and 4 ligands of same type and 2 ligands of different type. So it is 4 plus 2 combination you observe over here. If it is 4 plus 2 combination, then in what all ways can you observe, or in what all ways can you arrange the ligands around the central atom? So arrangement number 1, or possibility number 1, I might choose to arrange all the 4 ammonia groups adjacent to each other and both the chlorines adjacent to each other. So in this, I have all the groups of similar types being arranged adjacent to each other. And in the second possibility, we have taken both the chlorines being opposite to each other and remaining ammonia groups occupying the rest of the positions. So this is possibility number 2. But technically speaking, other than these two, we have third possibility also. You can arrange the groups in this manner also. Cobalt at the center and chlorine not in adjacent positions, and ammonia occupying the remaining positions as you see here. But when you compare this arrangement, in this arrangement, what do you get to see? You get to see chlorines being non-adjacent to each other, isn't it? But in the possibilities that I have considered chlorine being adjacent and chlorine being opposite. But in the possibility that is written over here, possibility number 3 is like in between the first possibility and second possibility, isn't it? Chlorines are very adjacent to each other. They are like friends with each other, and then they moved a little apart and then they went opposite to each other. So in case of this 4 plus 2 heteroleptic complexes, to observe geometrical isomerism, you take two extremities. You take extremely close and you take extremely opposite. If you are having two groups or all the groups of same type being adjacent to each other, call it as cis isomer. If you are having all the groups being non-adjacent to each other or opposite to each other, call it as trans isomer. Then what about this isomer that I have written? This we do not consider. Why? Because this is between cis and trans. It is not completely cis because you don't have the chlorines being adjacent. So it's not completely cis. It's not even completely trans because you don't even have chlorines being opposite, isn't it? So the two ligands of the same type, if they are adjacent to each other, it is cis isomer. If they are opposite to each other, it is trans isomer. If it is between both of them, it's neither. It's not cis, neither trans. It's not a complete trans form, or it's not even completely cis form. So we don't consider this combination. This is like in between cis and trans, so ignore this. Consider the extremities. If the two ligands that you see of same type are adjacent, call it as cis. If they are opposite, call it as trans. So this is geometrical isomerism type 1, which is called cis-trans isomerism. But then, as I told you, what if you have a ligand arrangement in this combination? What if you have a heteroleptic complex where you have 3 ligands of one type, 3 ligands of another type? What do? What kind of geometrical isomerism this kind of complexes exhibit? Or do they not exhibit geometrical isomerism at all? The answer is they exhibit geometrical isomerism, but they don't exhibit cis-trans. But there is another type of geometrical isomerism called as Fachner isomerism, facial meridional isomerism. So this combination, when you have a coordination number 6 in a heteroleptic complex and 3 ligands of same type and 3 ligands of other type exist, when you see this 3 plus 3 combination, cis-trans geometrical isomerism doesn't exist, but Fachner isomerism does exist. Let us observe that Fachner isomerism over here. Alright, so observe, you are talking about a complex wherein you are having cobalt acting as a central atom and you are having NO2 taken 3 times, you are having ammonia taken 3 times. This is your complex, right? So this basically is 3 plus 3 arrangement of ligands. In this, you might take the central atom like this at the center, and you might arrange 3 ligands of same type adjacent to each other in an octahedron, or you might also choose to arrange 3 ligands of same type non-adjacent to each other. If you are having 3 ligands of same types adjacent to each other, you call it as facial isomerism. And if you have them non-adjacent to each other, you call them as meridional isomerism. So it is facial meridional isomerism. This Fachner or facial meridional isomerism is a kind of geometrical isomerism, and this is only seen when you have a complex which is heteroleptic by nature and in which you have 3 plus 3 arrangement of of ligands. 3 ligands must belong to one type and 3 ligands must belong to the second type. When you have this kind of arrangement of ligands, you get to see this facial meridional isomerism. So facial isomerism is when 3 ligands of same type are adjacent, and meridional is when 3 ligands of same type are non-adjacent to each other. I hope you're clear with this. And here is one more example to observe cis-trans isomerism. Cis-trans isomerism in case of COCl2 En taken twice complex. In case of the ligands which are divalent by nature, also we can observe this kind of cis-trans isomerism. Central atom, and around the central atom, when you look at the ligands, if you have 2 ligands of same type adjacent, call it as cis. If you have 2 ligands of the same type being opposite, call it as trans. Alright, so this is about cis-trans isomerism and Fachmer isomerism. Let us quickly summarize this and then we'll go ahead with optical isomerism. So basically isomerism in complexes can be of 2 types, structural and stereo. In stereo isomerism there are 2 types further, geometrical and optical. Geometrical isomerism deals with arrangement of ligands around central atom, adjacent or non-adjacently. So this geometrical isomerism can be further classified into cis-trans and Fachmer isomers. So cis-trans isomerism is observed in case of those complexes which are heteroleptic by nature, in which you get to see 4+2 arrangement of ligands or maybe 2+4 arrangement of ligands. You need to be having 4 ligands of same type and 2 ligands of different type if you talk about coordination number 6. And this also can be observed in the complexes where coordination number is 4, where the combination should be 2+2 arrangement. Okay? And on the other hand, Fachmer isomerism also is seen in case of heteroleptic complexes only. And over here the arrangement, the coordination number should be 6 and arrangement of ligands should be 3+3. 3 ligands of same type and 3 ligands of different type. If ligands of the same type are adjacent to each other, call it as cis isomerism. If they are opposite of each other, call it as trans isomerism. On the other hand, in Fachmer, if the ligands are arranged adjacent to each other, call them as facial isomers, and if they are non-adjacent, call them as meridional isomers. So this is about geometrical isomerism. Now we are moving on to optical isomerism, which is the next type of stereo isomerism. And optical isomerism basically is observed due to some conditions. You need to have some conditions satisfied to see optical isomerism. Let us understand those conditions first of all. So optical isomerism can be observed only in case of those molecules which have capacity to produce non-superimposable mirror images. If you have a molecule which have capacity to produce non-superimposable mirror image, that molecule is optically active. That molecule can participate in optical isomerism. So now we need to understand what exactly is this mirror image that we are talking about. You might have seen yourselves in mirror, right? So the image of yours that you see in the mirror is referred as mirror image. So instead of you, if I take an alphabet, say I have an alphabet like O and I'm placing it in front of mirror, I'll see the flip side of the O in mirror, isn't it? So this is original and this is mirror image, right? So now if I take this mirror image, just imagine I'm watching it from the top and this is the top side of the mirror image, alright? So I'm taking this mirror image and I'm keeping the top side facing the sky and I'm imposing this mirror image on original. And when I impose this mirror image on original, I realize that the original form of O and its mirror image, both of them look alike. There's no difference between them at all. So when I place the mirror image on the original, keeping the top side of the mirror image facing the sky, the original and mirror image, if they look alike without any difference, I call that condition as superimposable. So superimposability or superimposable is being able to place the mirror image on the original just the way it was in the mirror, and even after placing it over original, if they match with respect to their size, shape, arrangement, every single thing, then you call them as superimposable. And this kind of superimposable molecules are optically inactive. They are what? They are optically inactive, and if they are optically inactive, they don't participate in optical isomerism. So these superimposable mirror images have no optical isomerism. Let us take one more example to get this better. This time I'm taking an alphabet B and I take the mirror image of B. When I take the mirror image, I get to see the flip side of B like this. So if I place B in front of the mirror, this is what you get to see. So this is original and this is mirror image. And now what am I doing? I'll first of all observe the top side of B. This is how it looks like. And I'll take this mirror image as it is and I'll place it on the original. When I take this mirror image as it is and when I place it on the original, you observe and tell me, are these two structures of B, the original and mirror image, are perfectly matching with each other or are they not matching with each other? The answer is, of course, they are not matching with each other. Look at the red structure, look at the black structure. They are facing two opposite sides. The lobes are facing two opposite sides. So the original and mirror image are not matching with each other when they are placed over one another. When you are placing mirror image on the original as it is, it's not matching to that of original. So this condition is called as non-superimposability, and these structures are called as non-superimposable structures. The alphabet B produces a non-superimposable mirror image. And that's why alphabet B is optically active. It is what? It is optically active. So it involves in optical isomerism. This optical isomerism that you see here produces optical isomers. Then what are optical isomers? This original and mirror image that you see here are optical isomers of each other. The original optical isomer and the mirror image is the second optical isomer. So there are two types of optical isomers. One is dextro isomer, which is small d, and the other one is levo isomer, which is small l. Dextro and levo isomers together are called as optical isomers. The way we called cis-trans isomers to be geometrical, FACMER isomers to be geometrical, we are calling DL isomers to be optical isomers. Alright. So optical isomers basically are non-superimposable mirror images of a molecule. Let's understand this with the help of a molecule. Observe this. Observe the complex. We are taking COEN thrice complex as an example. And this is the structure. Here you go with the cobalt central atom. This is EN1, EN2 and EN3. When I take the mirror image, I get to see the flip side of this molecule. So central atom is here, EN1 is here, EN2 is here and EN3 is here, right? So now what am I trying to do is, I'm just trying to superimpose this mirror image onto original. This is original, right? And I'm trying to superimpose this mirror image onto original. So I'll have the cobalt in place, but I'll be having EN1 over here, I'll be having EN2 over here, I'll be having EN3 over here if I try superimposing mirror image onto original. And now when I observe the relation between the original and the mirror image, they don't coincide with each other. EN1 is over here, but in original EN2 is here, opposite. EN2 and EN3 are also taking the same places, right? So the groups in mirror image and the groups in original are not matching with each other. Because they are not matching with each other, we call the condition as non-superimposability. So this molecule, this complex that you see here is producing non-superimposable mirror images. And any molecule that produces non-superimposable mirror images are called as optical isomers. So here original is one optical isomer, which is dextro or D form, and the second one, the mirror image, is the second optical isomer, which is L or levo isomer. I hope you could understand this better. For you to understand this in much more detail, let's take one more example and observe. Say I'm talking about another complex, and the complex is PtCl2En twice. So you have two chlorines and two enes over here. Now don't merge this concept with geometrical isomerism. Having adjacent chlorines is cis form, not having adjacent chlorines is trans form. No, we are not talking about that concept. So check that. So over here we are just observing about optical isomerism. And how do I know when a molecule can exhibit optical isomerism? For this, the condition is the molecule should be able to produce non-superimposable mirror images, right? So take the mirror image and check if it is superimposable or not. So first of all, the original image or the original molecule is this. central atom here, and you are having two chlorines, chlorine number, chlorine number 1, chlorine number 2, and ene number 1, ene number 2. And when I take the mirror image, it is the flip side of original, and in this mirror image I see chlorine number 1 here, chlorine number 2 here. The position of chlorine 2 changed, and ene 1 here, ene 2 here. And when I'm trying to superimpose the mirror image on original, what do I see? I'll see platinum in place, but then chlorine number 2 comes here. Chlorine number 1 is here itself. Then what about ene 1? Ene 1 is here and ene 2 is here. When I observe the position of the groups around the central atom in the mirror image and in the original, I don't see them matching to each other. Now if you ask me, but chlorine is matching, but matching of one group is not sufficient. You need to have all the groups matching as it is, exactly, even without 1 point of difference. Only then you call it as superimposable. But here only one chlorine is matching, rest everything is different. So this particular complex is producing non-superimposable mirror images. Because non-superimposable mirror images are produced, this molecule is exhibiting optical isomerism. So how many types of optical isomers are possible? Optical isomers can be of two types. One is D isomer or dextroisomer. The second one is levoisomer. So this molecule is producing dextro and levoisomer. By the way, these optical isomers are also called as enantiomers. In some books you get to see them being written as enantiomers. So don't get confused. So this complex that you see here is optically active. It is exhibiting optical isomerism, which is D isomer and L isomer. The original is D and the mirror image is levo, L isomer. I hope now you could understand optical isomerism in detail. But in case you have any doubts about this, you can always ask your doubts in the comment section below. Now let us quickly summarize and move ahead. So here we were talking about isomerism in complex compounds. Isomerism can be of two types, structural isomerism and stereoisomerism. Structural isomerism has already been discussed in part 1 of this video. If you have not seen the video, the link is available in the description. And the second part of the video was talking about stereoisomerism. This is the second part of the video. So in stereoisomerism, we are talking about two types, geometrical and optical. Geometrical can be further classified into cis, trans and phagma. Optical has got only one type, which is DL, dextro, levo. And the conditions are important for each type of isomerism. When can you say the molecule is exhibiting linkage isomerism? Here are conditions, and we discussed the conditions in the video in detail, right? Similarly, when can you say a molecule is exhibiting geometrical or cis, trans or optical isomerism? Learn the conditions so that it gets easy for you to understand and remember these concepts. I hope this video helped you understand stereoisomerism in complex compounds. I'll see you in one other video. Until then, bye.